You can all see the screen. Thanks for the introduction, Natalie. So today I am very excited to tell you about a very interesting galaxy cluster in the Massive and Distant Clusters survey called MaDCoWS. And it is particularly interesting because it has high radioactivity. So we have a lot of radio data in various wavelengths, and some of it being the GBT. So today I would like to take you along on the journey of discovering why this galaxy cluster is interesting and why it has high radioactivity. So first, a bit of background. Okay, so for you to understand why this galaxy cluster is interesting and why the high radioactivity is also interesting. So a bit of background on galaxy clusters. So there can be hundreds to thousands of galaxy members in a cluster, but those members only make up a few percent of the total mass of the galaxy cluster. So in fact, 80 to 90% of the mass of a galaxy cluster is dark matter, and 10 to 15% is actually hot gas that we call the intercluster medium. And these galaxy clusters typically have masses of 10 to the 14 solar masses and greater. And cosmological simulations tell us that in the local universe, 30% of all galaxies are in a cluster or a group. So this is an important environment to understand galaxy evolution in order to understand galaxy evolution as a whole. One type of galaxy that can exist in a galaxy cluster is an active galactic nuclei, or an AGN. And these are known for their very high energies. So at the center of a galaxy, so here we see an elliptical galaxy, there can exist an AGN engine, which emits a substantial amount of radiation that cannot be explained by either star formation or the interstellar medium or the interaction between the two. And it emits a large amount of radiation. And so at the very center of this galaxy, there's this AGN engine. And this physical scale is actually very small. So it's only 0.002% of the entire physical size of the galaxy. And so you have the black hole, the accretion disk, and then also the jets. So you have matter from the accretion disk falling onto the supermassive black hole and then being expelled in these jets. And in the radio, we can typically see these very, very beautiful jets that come out much, much further than the galaxy itself. So the AGN are one type of galaxy that can be in a galaxy cluster. And even though there may only be a few of them, or it's a small percent of the number of galaxies that are in a galaxy cluster, they can have a very large effect on the cluster and the galaxies within the cluster as well. So here we're looking at a galaxy cluster, and at the center is the largest galaxy in the cluster, and all of these are points. All these points of lights are galaxies themselves. And you can see here the beautiful radio lobes that are coming out from the center of the cluster and from that AGN in particular. And it's interacting with the intercluster medium in the cluster. So this is very interesting because AGN and the cluster environment, they interact between one another. We want to understand that interaction in more depth. How does the cluster environment affect the production of AGN, and how do AGN affect the environment? So something that's interesting is that as you go further back in time and as you increase with redshift, the number of AGN within a cluster, or the fraction of galaxies that are AGN in clusters, increases as a function of redshift. And it particularly peaks at a redshift of about 1. So the epoch of Z of about 1 is a very interesting epoch to understand and investigate this correlation between active galactic nuclei and the cluster environment. So that is exactly what we have created. We have created a sample of galaxy clusters at this redshift, and that is the Massive and Distant Clusters of WISE survey, or MaDCoWS. And so we've created this galaxy cluster catalog at this important epoch by cross-correlating infrared data with optical data, and then performing magnitude and color cuts in order to isolate the galaxies at this particular redshift. And then we apply a smoothing kernel, and then from the density map of the remaining sources, we are able to find about 2,700 galaxy clusters. So this is a fantastic sample that we can use to carry out many interesting statistical investigations into the correlation between the cluster environment and all sorts of things like the galaxy cluster populations, and something I'm particularly interested in, of course, is the AGN population. So a few studies that I have carried out is a couple different projects that was investigating the relationship between particularly radio AGN and this cluster environment. So we identified a sample of about 50 MaDCoWS clusters that had radio sources within the center of the galaxy cluster. And then we followed those up with VLA, and that's how we produce these radioactive cows, these radio observations of active galaxies in MaDCoWS clusters. And we observed them over 3 semesters in 2 bands. And then we were able to look at all of these clusters and the radio sources in these clusters. And that's how the cluster that I'm going to talk to you about today was identified as a special cluster. So you may be wondering, what type of radio emission would you expect to see in a galaxy cluster, and what would the morphologies be, etc. So one type of emission, radio emission that can come from a galaxy cluster, are these large diffuse types of emissions. So you have radio halos, which are here at the center of the cluster and are very diffuse. And then you can have these radio relics, which appear as arcs on the outskirts of the cluster. Then you can have the synchrotron radiation from AGN, which I've been talking about already, and they can come in various flavors and morphologies. So some very typical ones are these morphologies called FR1 and FR2. I won't go into much detail, but you can simply just see this, these images here. So the FR2s have these characteristic bright, beautiful lobes where the center of the host galaxy is here, and then the lobes extend outward. Then you have FR2s, where most of the radio emission is near the center, and then becomes more diffuse as you go further out. And then you can also have these hybrid morphology radio sources, or HIMORs, that as a combination. So you have an FR2 in the bottom and an FR1 at the top. So these radio AGN can actually become bent, in fact. So here we have the central galaxy, and these are the jets coming out, but they become bent. So these are called narrow angle tails. And this happens by the galaxies in a galaxy cluster have a velocity. And so as they travel around the galaxy, this creates pressure as it is interacting with the inner cluster medium, and that bends the jets backwards. You can think about it as you're driving in a car and you go faster and faster and your hair just whips behind you. Sort of similar to that. And with these head-tail radio galaxies, they are traveling so quickly that the 2 jets, in fact, become 1. And then there are these fundamentally different types of bent tail radio sources that are the wide-angle tails, or WATS. And these are different because their host galaxies are near the center of the cluster, and thus do not have a large velocity relative to the intercluster medium. And so that can't explain the bending of these radio lobes anymore. So instead, it has been theorized and found that, and investigated as well with observational studies, that it's instead, these happen in a merging cluster environment. So you have 2 structures merging together, and so you have the intercluster medium is very chaotic, and that can, so the medium itself is moving instead of the galaxy, and so that creates these bent sources. So that's a brief overview of the types of radio emission you might expect to see in galaxy clusters. So these are the 50 sources in the MaDCoWS clusters. There are all sorts of morphologies, but I'm not here to talk to you today about that. I just wanted to give you a broad context of this particular galaxy cluster, so 1506. So this one was very interesting because it stood out in several different ways. So first of all, it stood out in that it was one of only 2 clusters in the 50 radioactive cows that had 5 radio sources in the cluster at all in the VLA data. It also is one of only 2 clusters that have 3 complex sources, which is quite interesting. And it is the only cluster that had 2 bent tail sources in the cluster at all. So this is the VLA data in the background. We also have some fantastic data from a lot of different wavelengths. So we have optical and infrared, and then 3 different frequencies in radio. So we have the LOFAR survey data, and then 2 bands of VLA, and then Mustang data. And they're all very important for the work that we have done with this cluster. So first of all, let's look at these sources and see what they are. So this indicates the center of the cluster. So we have this source here is categorized as a FR2. And then we have this bent tail source. You can see they have the center of the host galaxy and then the bent lobes. Another source that is also a bent tail, but it also is very close to the center of the galaxy. So we categorize it as a wide angle tail. It also seems to be this hybrid type where it has an FR1 side and an FR2 side. And then we have 2 point sources as well. So as I mentioned, we also have infrared data, which we can then identify the host galaxies. I'm not going to go into too much detail, but we were able to identify the host galaxies and also confirm that they are with some just different data analysis types. We were able to confirm that they are in the cluster, these host galaxies, and that they are among the most massive in the galaxy cluster too. So the question still remains, why does this cluster have high radioactivity? And so there are 2 different approaches for this. There's first the large scale environment. Perhaps it is something about the cluster environment that is inducing this high amount of radioactivity, or perhaps it's the small scale, something happening on the galaxy level. But we have several lines of evidence that indicate it's the large scale environment that is facilitating this high radioactivity. So we actually have 3 lines of evidence that 1506 is a merging galaxy cluster system. So I'm going to go through each of those. So first of all, we can look at the spatial distribution of the galaxies. So each point here is a galaxy that is at the particular redshift. And then this is a density map. So at the center, you have a high density of galaxies. And then as you go further out, the contours show you have less, a lower density. So you see the main cluster here, and this circle indicates 1 arc minute around the cluster center. But then you'll notice that we have a subsystem up in the left-hand corner. So there's also one down here as well, but this one is much more pronounced. So this indicates to us that this is a merging system, and this is the axis of merger of the merger. So you have the main cluster and then the substructure. So we also can look at the morphology of the radio jets in particular. And so we have those 2 bent tail sources. So that does indicate a chaotic environment. And in particular, this source, it has a couple different classifications that indicate a merging system. So first of all, what type of bent tail source? Well, it seems to be a wide angle tail because it is very near the cluster center. So it's not moving very much with respect to the other galaxies. And if you remember from what I was talking about earlier, these wide angle tails seem to occur in merging environments, because the intercluster medium is what is responsible for the bending of these sources due to the chaotic environment. So this source can also be categorized as a hybrid morphology radio source, because it has this FR1 on one side and FR2 on the other side. And these hybrid morphology radio sources are relatively rare, and they have been theorized to also indicate a very chaotic environment, an emerging environment, because how could you create two different types of morphology of the jets on each side of the galaxy? And it's thought, well, that there's different external conditions that would create this. So this also points to a chaotic emerging system. And then lastly, we also notice an asymmetry in this source. So we have, it's more bent on one side than the other. So we have this asymmetry. So that can also be explained by a merging environment. So you have the radio source at the center, and then if you have the merging system and the substructure up here, and that will then create this difference in the density in their cluster medium, because you have more substructure and more material on this side as opposed to this side. So that could create this asymmetry and also high morphs. So the morphology of these sources also indicate that it is a merging galaxy cluster. And then what you all care about and are excited about is that we have the GBT data. So this allows us to get the mass of the cluster, and that's through this SZ effect. So this happens when, so we're observing the cosmic microwave background photons. They interact with the intercluster medium in the galaxy cluster, and those photons then gain energy, and then you see a decrement then, because those photons are no longer seen at these various frequencies. So that's what we see here in the GBT data. We see this decrement where the galaxy cluster is. And then we also see these point sources where the radio sources are. So this decrement is proportional then to the mass of the galaxy cluster. And for these MaDCoWS clusters, we are able to have, we have the mass gotten from the SZ effect, and then the number of galaxies, which we get from the infrared data. So you count the number of galaxies within a certain radius, and they form this mass richness relationship. So this relationship between the number of galaxies and the total mass of the cluster. And you'll notice that a few of them lie off the relation, and these we have Chandra data for and are indicative of being galaxy cluster mergers. And we have the mass from the GBT of this cluster, and that places it in this regime of merging galaxy clusters. So we have a larger program of observing MaDCoWS clusters with Mustang to get their masses. So we have 15 to 20 now, and those results are being published by Simon Dicker. And Move 1506 was one of the first to get a mass from that work. And so that puts that in the merging cluster regime. So why does it make sense that the merging clusters would be over here? So I wanted to show that a bit more intuitively. So if you observe, the final galaxy cluster will be here in the center. And if you observe the number of galaxies that inside of this circle, and also what the intercluster medium, or this red part, is doing throughout time, you'll notice that the number of galaxies, you can see that that increases much sooner than the ICM coalesces into one. So we see that the number of galaxies increases in a merging system before we are able to observe the SZ, a stronger SZ effect from the coalesced intercluster medium. So then that was just a quick explanation of why we would expect mergers to be over there. So we have these 3 lines of evidence that this cluster is a merging system. We have the spatial distribution of the galaxies, and we saw the subsystem. Then we have the radiomorphology of the jets, indicating a chaotic environment and a merging system. And then also the mass richness relation, where the mass and number of galaxies of this galaxy cluster lies. And so this all points to that the dynamical state of this galaxy cluster is affecting the radioactivity of the galaxies themselves. So it seems that what is special about this cluster, well, it's a merging cluster, and it seems that it's the large-scale environment that is facilitating this high radioactivity of these clusters. So going forward, it'll be interesting to investigate more of the galaxy clusters to find merging systems and to see further if a correlation does truly pop out at a higher statistical significance to if the merging systems really do increase the radioactivity. And this has been seen in the literature before as well. So that is my talk, and this is a quick summary. So the 1506 has a high radioactivity with 5 radio sources. The host galaxies are in the cluster and are amongst the most massive galaxies, which is in line with work before. And based on these 3 lines of evidence, the spatial distribution of galaxies, the radiomorphology, and the mass from the GBT, this is a merging system. And it seems that during a merger phase, radioactivity can be dramatically enhanced from this merger. So thank you, and I'll take any questions.
Hi, Emily. I guess I have a question. How do you draw the distinction between what is classified as a galaxy cluster versus a galaxy group? Is it the mass of like the, I guess, environment, or is it the number of members? How do you make that distinction?
Yeah, that's a great question. Yeah, it is the mass. It's the total mass of the system. So the line is typically drawn around 10 to the 14 solar masses. So yeah, and also, I mean, that's the main thing, but then there's also the clusters usually have a much higher prominence of the intercluster medium as well, so you have that hot gas, whereas groups typically don't have that as much.
So I'm sorry I missed the beginning. So how far away are these? Is this merger that you're seeing, and what would do you seek more distant cluster mergers, or what's the research?
That's a great question. So it's at a redshift of about 1. So that's an epoch when galaxy clusters are still assembling and merging. So it's not surprising that we're seeing a merger at this epoch. And as you go further back and go at higher redshift, you'll see more and more mergers as well. But the interesting part here was that we were seeing this correlation between the merging system and that it had high radioactivity.
So would you expect then you could, like, say at z=2, could you find clusters with this, or do you think that would, I mean, if you see a collection of sources?
Yeah, so in general, it's known that the cluster environment increases the number of radio AGN that occur in them. So, and as you go in the local universe, you expect to see less merging systems. So something I would like to do is get a larger sample of merging clusters and look at their radio AGN population. So guess to more directly answer your question, at lower redshift and in the local universe, the causation wouldn't necessarily be because it's a merging system that you would have the high radioactivity. And at lower redshift too, normally you have these ginormous radio AGN at the center of the cluster, whereas because the cluster has had time to fully form, but as you go at higher redshift, you have a more chaotic system, so it makes sense that you would have things, the AGN spread out a lot more, so the radio AGN in particular. Any other questions?
I guess I had one more. What do they think is causing the AGN activity in these high redshift galaxies? Like, since it seems like it's a little bit after when you saw the peak of star formation in the universe, do they think that maybe star formation and feedback could be feeding the AGN activity, or is there any thoughts on like what is causing the high activity you're seeing in these galaxies?
Yeah, so what we think is that it's the perturbation of the cold gas disk that forms in galaxies. So in the cluster, you'll have a lot of activity, and as I was saying, you know, this merging system, so you have the opportunity to perturb the cold gas disk and then thus create the AGN. So yeah, that's what we think currently.
Thanks.
Mm-hmm. Okay. Well, it was great giving you all a talk, and I hope you found it interesting.
Thank you for giving the talk today, Emily.
Yeah.
And we will meet back here again next week at 12:15. The talk next week is going to be given by DJ Pisano, who is going to give an overview on the key science goals for FLAG and the instrumentation. All right, thanks.
Thanks.
Thanks, Emily.
Of course.
Thanks and cheers.